Hello everyone, welcome to another ALP video. I'm Kevin, and today we'll be covering Vieta's formulas. So first of all, what is Vieta's? Well, basically, Vieta's is a way to relate the coefficients and roots of a polynomial. And here on the screen is the statement of Vieta's. If we have the coefficients of a polynomial, we can write certain sums of the roots as a quotient of two coefficients. So if we have a polynomial f of x equals an xn plus an minus 1 x to the n minus 1 plus so on all the way down to a1x plus a0, and the roots are r1, r2, all the way up to rn, then we have the following sums. So on the left-hand side of these equations, we have the kth symmetric sums of all the roots. In other words, we multiply k of the roots, and then we add them up over all possible products of k. For example, in this first line, k equals 1, and we basically just take the product of one root. So that's just basically taking one root at a time, and we just add them all up, right? So this is just the left-hand side. And on the second line, we take the product of all possible pairs of two roots, and then we multiply them together, and then we add them all up, right? So on the third line, we take the all possible products of three roots, and then we add them all up. And in general, there will be n choose k terms on the left side, where k is the number of the equation. So for example, in the third line, there will be n choose 3 terms, right? Because we're taking 3 roots at a time. And keep in mind that these roots can be duplicates. So for example, we can have r1 equals r2 and so on. And over here on the right-hand side, we always have an in the denominator, and then the sign alternates, right? So in the first equation, it's negative. The second one is positive. The third one is negative, and so on. And then the numerator is an minus k, right? So for example, in the first equation, it is an minus 1, second equation, an minus 2, and so on. So as a quick example, let's say we have n equals 3. Then our polynomial would be f of x equals a3 x cubed plus a2 x squared plus a2x squared plus a1x plus a0. And the roots would be r1, r2, r3. So basically what Vieta's would get us is r1 plus r2 plus r3 is equal to negative a2 over r3, right? Because the denominator is always going to be an, which in this case is a3. The sign starts off as negative, and the numerator on the right-hand side is going to be an minus 1, which is a2. And on the left-hand side, we just have the sum of the roots. And for our second equation, we will have r1, r2, plus r1, r3, plus r2, r3, right? So the all possible products of two different roots at a time, and that will be equal to a1 over a3. And on the third equation, we will just have r1, r2, r3 is equal to negative a0 over a3, right? Because we basically take the product of three different roots and we add that up over all possible triplets of roots. But since there's only three roots, we only add one possible triplet of roots. Okay, so that's kind of what Vieta says. And the idea behind the proof is basically we just write the polynomial in standard form and also in factored form. So standard form is just the an x to the n plus an minus 1 x to the n minus 1 form. And factored form is just basically an, so times x minus r1 times x minus r2, right? So basically the product of all the roots pretty much. And then we have this an at the beginning because we need the leading coefficient to be a of n. And then if we just expand this expression out and we compare the coefficients to the standard form, then we'll basically just get all of Vieta's formulas. And this, in general, this is just one of the reasons why polynomials are so important. And because there are a lot of different ways to express them, right? So here we've seen the factored form and the standard form. And when you kind of switch between these multiple ways of expressing polynomials, we get a lot of powerful equations that we can use. Okay. So now let's see a few examples. This first one is from the AMC 12A 2017, right? So if we read the question, for certain real numbers ABC, this polynomial g of x has 3 distinct roots, and each root of g of x is also a root of the polynomial f of x, and they're asking for f of 1. So note that we have a lot of information about the coefficients of g of x, right? In particular, we know that the first coefficient is just 1 because there's no coefficient, so that's the same as having 1x cubed, right? That's just equal to x cubed. And this coefficient is 1x, and the last coefficient is just a 10. So we're given info about the coefficients and we want to relate that to information about the roots because we want to know what the roots are, right? So let's say the roots of G are going to be R1, R2, R3, right? So these are the three roots of G. And then Vietas will basically give us that R1 plus R2 plus R3 is going to be equal to negative A. And then then R1 plus R2 plus R3 plus R4 is equal to -1, where R4 is the fourth root of f of x, right? So R1, R2, R3, R4 are the roots of f. And in particular, R1, R2, R3 are the roots of G, since the roots of G are all roots of x, or are all roots of f as well. Okay. So in particular, these two equations gives us that R4 is going to be equal to a minus 1. Okay. Because we can just subtract the first equation from the second. And then Vietas on G also gives us that R1, R2, R3 is equal to -10, right? And R1, R2 plus R2, R3 plus R3, R1 is going to be equal to it's going to be equal to +1 because it is the coefficient of the x term divided by the coefficient of the x cubed term, which is just 1/1. Okay. And then we can also do Vietas on f, and that will give us that R1, R2, R3 plus R2, R3, R4. So I'm taking the product of 3 roots at a time and summing that up, right? Plus R1, R3, R4 plus R1, R2, R4. This is going to be equal to the coefficient of x, which is 100, divided by the coefficient of x to the fourth, which is 1, and then take the negative of that because signs alternate. So this is going to be -100. Okay, and then this last equation actually simplifies a lot because, for example, we can plug in this equation into the last equation, and the first term just becomes -10. And then we can factor out an r to the fourth, or sorry, R4 from the other 3 terms. And we get R4 times R2, R3 plus R1, R3 plus R1, R2, right? And that is equal to -100. But we also know what this term is over here. This R1, or R2, R3 plus R1, R3 plus R1, R2. That is just equal to 1, right? Because we already had that equation over here. So in particular, what that gets us is, if I just move up to the top, that gets us that -10 plus R4 multiplied by 1, right? Because this standard expression is just equal to 1. That is equal to 100, or -100, sorry. And then we can just substitute in our expression for R4, and we get -10 plus a minus 1 is equal to -100. And in particular, a is equal to -89. Okay. And then once we know what a is equal to, we can just find everything else pretty much, right? For example, we know that f of x, I'll just clear everything. So, and then we know that a is equal to -89, right? And we know that f of x is going to be equal to x minus R4 multiplied by g of x. This follows from factor theorem because we can basically factor out the x minus R4 since R4 is a root, right? And we knew that R4 was equal to -90, which I erased, but established that earlier. And then we can just multiply the standard expression out because we know what g of x is since we know what a is, right? And then we can just multiply it all out. Or alternatively, we can just plug in 1 directly for x since we want f of 1. And that will give us 1 plus 89 multiplied by, 1 plus 90. 1 plus 90 multiplied by g of 1. And g of 1 is just going to be 1 cubed plus a times 1 squared plus 1 times 10 plus 10. And since we know what a is, we can just evaluate this expression directly, and we will get -7,007, I believe. Okay. So that is it for this problem. So let's see a second example from the 2008 EME 2, right? So once again, if we look at the question, we'll notice that the first thing is we're given information about these coefficients. In fact, we know all of the coefficients and we want information about the roots. So that is usually assigned to use Vietas. So we could actually just expand the standard expression that they want, and we'll get a really ugly expression, but technically we could use symmetric sums and find it using Vietas. However, that is rather tedious, so we'll try to look for a better solution. So we'll start by noting that r plus s plus t is going to be equal to 0 because it is equal to the coefficient of the x squared term divided by the coefficient of the x cubed term, and then the negative of that. So that's just negative 0 over 8 since the x squared term is non-existent. So the coefficient is basically 0, and that will just be 0, right? And in particular, if we substitute in, for example, this gives us r plus s is going to be equal to negative t. So the expression that they want, that's just negative t cubed minus r cubed minus s cubed, right? Since r plus s is negative t, s plus t is negative r, and t plus r is negative s. Okay, but we can also notice that by definition, for example, let's consider t cubed. By definition, 8t cubed is equal to negative 1001t minus 2008. And the reason this is true is because t by definition is a solution to the equation 8x cubed plus 1000x plus 2008 equals 0. So we can just shift the 1000x plus 2008 to the other side of the equation. Right. Okay. So in particular, we can divide this by 8, and then we can substitute into this negative t cubed plus minus r cubed minus s cubed. And we basically get that we just want to find 1001 times r plus s plus t divided by 8 plus 2008 times 3 divided by 8. Right, so I skipped a bit of algebra here, but basically the idea is we just substitute in this expression for t cubed into our negative t cubed minus r cubed minus x cubed expression and do the same for r and s. But we know that r plus s plus t is 0, right? So this first term basically just goes away, and all we're left with is just 2008 times 3 over 8. And that is just going to be equal to 753. So that is our final answer. Right. Okay. So now let's move on to our final example, which is from the 2019 AME 1, so relatively new example. And I believe this was problem 10, so relatively tricky. Okay, so once again, if we look at the problem, we have a lot of information about the roots of this polynomial, right? Because by factor theorem, z1, z2, all the way up to z673, these are all roots of the polynomial. And not only that, they are all triple roots, right? So because they appear 3 times in this factorization. So Vietas, and we also have information about the coefficients, right? We know the coefficients are 20, 19, and the first one is 1. And then after that, we don't really know anything else, but that's fine. Let's just keep working. Okay. So Vietas on this, on the sum of the roots is basically going to be z1 plus z2 all the way up to z673, right? Except when we add the roots, we actually have to multiply this by 3 because again, z1 up to z673 are all triple roots of the polynomial. And we have to count repeated roots when we're working with Vietas. So it's going to be 3 times this expression. That is going to be equal to negative 20 by Vietas because it will be the coefficient of the x to the 2018 term divided by the coefficient of the x to the 2019 term, which is 20 over 1, which is just 20. And then take the negative of that because signs alternate in Vietas. Right, so we get this equation. And then if we apply it to this 19 coefficient, basically what we get is we take the product of any 2 roots and we sum that out over all possible products of pairs of roots. So that will actually get us 3 times z1 squared plus z2 squared plus all the way up to z673 squared. Right, because this comes from basically taking 2 of the same root, because again, each root shows up 3 times, right? So there's 3 ways to choose 2 of the same root, right? So, and then when we multiply them together, we get the root squared, and then we have to multiply by 3. And then if we pick 2 different roots, there are 3 times 3 ways to do that. So that's just 9 ways to do that, because again, each root shows up 3 times. And we basically get the product of any 2 different roots, right? Which I will not write it all out, but you get the idea. And that is going to be equal to 19 because it is the coefficient of x to the 2017 divided by the coefficient of x to the 2019, which is just 1. And then we take the positive version this time because again, signs alternate, right? But you'll notice that this last term is actually exactly what they're asking for. even though the notation they use is rather intimidating, if you just think about this, they're basically just asking for the product of zj, zk over all possible distinct values of j and k, which is exactly what this thing is, right? So now we have this expression involving what we want to find, which is rather nice. So let's just set that equal to a, right? So set the expression that we want to find, we'll let that equal a. And then we'll also let this first expression over here, we'll let that equal b, just to save a bit of time, right? So basically what we get is we get 3b plus 9a equals 19. Okay, so now if we could find b, we would just be done because again, we're trying to find a here. But the question is, how do we find b, right? Well, there's some information that we haven't used yet. In particular, we haven't actually used this first equation, right? So if we try to figure out how to use this first equation, the thing to note here is that we need squared terms, right? Because b consists of the sum of squares of these zi. So, but this first equation does not have any square terms. It only has linear terms in zi, right? So we could just try squaring the first term and see where that gets us. And in fact, if you expand out this, if you square this first equation and expand it out, you will actually get that it is just equal to 9a plus 18, or sorry, 9b plus, you'll get that it's equal to 9b plus 18a. And on the right side, we obviously just have 400 because negative 20 squared, right? And at this point, you'll notice we actually just have a system of equations where we have two linear equations and two variables. So there's a very good chance that we can actually just solve this, right? And in fact, we can actually just solve for a and b here. And I'll skip the algebra, but basically you just get that a is equal to negative 343 over 9, right? And since this is the AME, we have to convert this into an integer. So let's see how they want us to turn this into an integer value. So first of all, they're asking for the absolute value of a, right? So absolute value of a will just be 343 over 9. And they want us to basically take the sum of the numerator and denominator. So 343 plus 9 is going to be 352. And that is our final answer. Okay. So in summary for Vietas, basically whenever we have information about coefficients or roots and we want information about the other, right? For example, if we have information about the coefficients and we want information about the roots, which is pretty much what we saw for all three problems here actually. But alternatively, if we have information about roots and we want information about coefficients, Vietas basically allows us to write a bunch of equations. And from here, the rest of the problem is usually just some algebraic manipulations. Okay. So that is it for this video. Thank you for listening.